today addresses at least a few of these first 4 points. So here's the outline. I'll talk about a generalized flux qubit, including the C shunt and the quarton, and then talk about a composite qubit that leverages non-adiabatic control. So as you know, we basically added a shunt capacitor to a persistent current flux qubit to improve its coherence times. And we started this effort by asking, what can we do to improve T1? And of course, there's basically two things we can do: reduce the sensitivity to environmental noise, or reduce the noise itself. And we can draw intuition from Fermi's golden rule, which has these two basic factors, one related to the dipole operator and the other related to the spectral density of the noise. And so if we look at the matrix element or the design first, we increase the capacitance, which has some positive aspects. It reduced sensitivity to charge noise and to stray capacitance. Of course, it has the negative that it's going to reduce anharmonicity, but the anharmonicity is still positive. Now, it's basically an LC circuit, so if we change C, we also have to change L to maintain the qubit frequency. And so we reduce the critical current, which has the plus that it reduces sensitivity to flux noise. That's good. But it also increases slightly the sensitivity to charge noise. Overall, it was a net win. So on the materials and fab side, or the noise or PSD side, we improved the capacitor film quality by basically by treating the substrate and also growing the metal in an MBE, and we've done some studies based on that, which are on the archive. And then one which is also a design aspect, I think, is to optimize the capacitor geometry to reduce the E-field participation. Okay, so these are the basic things that we did when thinking about the C shunt flux qubit. And so this just shows the net result that we got. On the left, there were 2 qubits coupled to a resonator, lambda over 2 resonator. This particular design was floating capacitor, but not all of them are this way. And the net results were that we got T1s around 50 microseconds and T2s that were about twice T1. And importantly, this was a much more reproducible design. I think that the previous flux qubits had shown some of the highest coherence times amongst the general family of superconducting qubits, but the reproducibility was very poor. Maybe 1 in 10 or 1 in 20 would have high coherence times, and the others would suffer from various aspects like stray capacitance and other losses. So we performed noise spectroscopy on this device in a number of ways, both using Ramsey interferometry, T1 row measurements, and looking at the T1 at the qubit frequency and inferring the noise spectrum that way. So what was really amazing to us is that this 1/f flux noise extends over many, many orders of magnitude. And the slope here is about 0.9. The amplitude is about 1.4 microfine out per root hertz at 1 hertz. And what we saw is that this lines up very nicely. This low frequency noise, which causes dephasing, intersects very nicely on this 1/f-like trajectory out at the qubit frequency, which indicates that 1/f flux noise, which we usually think of as dephasing, may also, depending on qubit design, of course, impact the energy relaxation of qubits. So it's also an energy decay mechanism. And so we took a lot of time to model this qubit because we wanted to look at how the qubit behaved as a function of different parameters, and also just to get an understanding of how reproducible it was. And so I'll just step through this briefly. What we have here is the decay rate 1/T1, and then again, this Fermi's golden rule, assuming these are all independent noise sources, and just add them all together, these rates. And so, we can start with the Purcell effect, where that's straightforward. We can measure the resonator line width, simulate the matrix elements, and this basically tells us the Purcell contribution to T1. To get a handle on the magnetic field or the flux noise, we designed a qubit that was highly sensitive to flux noise intentionally, and then measured the T1 as a function of the qubit frequency, and that's what's shown here. And from that by simulating the matrix element for this design, and then fitting the data that we measured, we were able to infer what the power spectral density was for flux noise, S phi. And so now we assume that we know that S phi. We then designed a qubit that was sensitive to charge noise and measured that T1 as a function of frequency. And now we know basically the charge noise spectral density, and it was proportional to, we presumed it was proportional to frequency. We tried some different models, white noise, proportional to frequency, proportional to 1 over f, and it was clear that the ohmic proportional to f is what matched well. And then finally, we looked at the variation in the temporal variation of the T1 as a function of time, and this allowed us to extract the noise spectral density due to quasi-particles. Okay, and so with all of these added together, we then went and made 20 more qubits of varying designs to exercise this model. And what you see here is measured T1 versus calculated T1. And the data points basically fall on the line that you see, indicating that what we measured was close to what we calculated. Okay, and this says, I think, two things. One is that the model seems to be pretty accurate, or at least captures the key decoherence mechanisms. But the other thing it indicates is that the fabrication is reproducible. We can make the design that we want to make, and that it, in fact, not only can we make it, but then when we measure it, we're not missing something, that it actually works. So that was published a few years ago in Nature Communications with Fei Yan as the lead author. Now, these quasi-particles, we then showed that if we apply some pre-pi pulses before we actually do an experiment, that we can improve the situation quite a bit. And so what you see on the left is basically a histogram of T1s as a function of time, both when we don't apply any pre-pulses, the red data, n equals 0, and when we do apply 5 pre-pulses, the blue data, n equals 5. And on the right, you can see, again, 0 versus 5 pre-pulses, and there you're seeing basically the T1 traces in the color plots. And you can see the left one looks quite noisy, but the right one looks quite clean. And if we take vertical slices of the standard deviation from trial to trial, you can see the red one, again, it's quite noisy, but the blue one is essentially flat. So, this looked like is a good way to at least pump away quasi-particles to get them out of the way. Okay, that's good, we can do that, but of course the question is, why are they there in the first place? And so I won't go into detail, but we've recently measured one potential source of these quasi-particles, and that's ionizing radiation from cosmic rays from space, and of course nuclear decay. It turns out that concrete has a lot of radioactive trace elements that can impact the qubits as well. And I'll just summarize here what you can find in this archive paper by Antti Vepsalainen from our group. Basically, ionizing radiation can lead to quasi-particle densities at the 10 to minus 8 to 10 to minus 9 level. So that's basically, Kyle Cerniak, who worked with Michel Devaray, they did some very nice experiments where they, basically shielded the thermal photons very, very well. And then what you're left with is basically 10 to minus 8 to 10 to minus 9. And it looks like that's consistent with what we're getting from ionizing radiation. Now, it's about half due to cosmic rays, half due to background nuclear decay. We can't shield cosmic rays with lead. We have to basically go deep underground for that. Now, what we also were able to show is that this will limit T1 of these current transmon designs to about 4 milliseconds. Now, there's a pretty big error bar on that, let's say 1 to 10 milliseconds, but it's in the millisecond range, and it also reduces dephasing. We did an experiment where we basically did Dicke radiometry or lock-in measurement by building a big lead shield that you see in the lower right and measured it down and then up and down, and basically did a lock-in measurement on a 10-minute period. And that's how we were able to infer this information at the top. But going forward, lead shielding, it's pretty heavy. That represents more than a ton of lead right there. Of course, moving underground also works, but that's deep underground. But I'm hopeful that what is interesting direction is let's design qubits that are less sensitive to quasi-particles, or use gap engineering to trap quasi-particles, or gap engineering to move them away from the junctions. So the upshot here is that ionizing radiation impacts today's transmon coherence at the 1 to 10 millisecond level, but that's if we don't do anything to mitigate it. And so working with Fei back in 2016 after the C Shunt, we were thinking, how can we generalize and create an engineering framework to understand qubits? And so that's what we're calling this generalized flux qubit. And we're only now just publishing this due to some unfortunate incidents that happened over the last few years, but Fei's back online and we're now publishing it. And what you can see is that all of these qubits on the left, transmons, persistent current flux qubits, fluxonium, C Shunt, can all be thought of as a primary junction in parallel with a number of inductive junctions and a capacitive shunt. And basically you have these design parameters. I won't read through them all. We all know what they are, including the number of junctions. I will mention gamma that I use here is basically the ratio of the big to the small junctions, which the persistent current flux qubits would think of as 1 over alpha. And the properties that we can design or get out are basically the qubit frequency and its anharmonicity, and then the sensitivity to the various types of noise. And we were just thinking, okay, what's a general framework that we can think about these different design choices, and are there rules of thumb or engineering guidelines that we can extract? And there are. And so what's shown on the right is a multi-dimensional phase space, such as the critical current, the total capacitance, the number of junctions n, this area ratio gamma normalized by n, and the various parameters that we design towards, like anharmonicity and the sensitivity to noise and qubit frequency. As you increase along any of these axes, the arrow indicates the direction of increasing, say, anharmonicity. So as you increase gamma over n, anharmonicity goes down, and et cetera for all of these. So I won't read through them all, but we're about to put this paper on the archive. And again, this is these are guidelines. It's not set in stone, and of course you have to simulate everything, but just to get an idea. And so based on this, one example that we decide to explore is something that Fei called the quarton. And the quarton is a primary junction with n parallel junctions and a shunt capacitance, but the number of junctions is chosen to be equal to gamma, or again, if you're thinking of alpha for flux qubits, it would be 1 over n. And essentially what we're doing is we're eliminating the quadratic term in the potential energy, leaving just a quartic potential, and that's why we call it the quarton. So you can see that if gamma is less than the number of parallel junctions, then that's basically like a persistent current flux qubit or fluxonium. If gamma is greater than n, then that's in the capacitively shunted flux qubit or transmon regime. But when it equals n, this is the quarton, where you have a truly quartic potential, or that quartic term is the leading correction to the potential. And when you do this, you can basically solve this simple Hamiltonian on the left. And what you find is that the anharmonicity for the quarton, okay, it's positive, but it's also about 1/3 of the qubit frequency. So if your qubit frequency is 3 to 6 gigahertz, then operating in the quarton regime will give about 1 to 2 gigahertz of anharmonicity. And we know that's substantially larger than what we get with the transmon and also the C Shunt flux qubit. So we made and measured a bunch of these back in 2016. I just show a picture of one of them on the left, which has 16 parallel junctions. It's made with the same fabrication process as the C Shunts. Substrate preparation was the same, and high Q aluminum, and this is a Dolan bridge style junction. Floating capacitor again. We reduced the critical current. These are 10 to 15 nanoamps, and we also reduced a bit the C Shunt. The EGA over EC is around or less than 10 for this device. Okay, so here's one example. I'm sorry, it's not the same as the previous one. This one has 8 junctions in parallel. But the results are the qubit frequency was about 3.6 gigahertz, and the anharmonicity was about 1 gigahertz. So that's, roughly this 1:3 ratio. Now, when we measured T1, we had expected it to be around 100 microseconds, and we got about half of that. So 40 to 80 microsecond T1, and also quite a bit of temporal variation, which can be attributed to quasi-particles, or as Google has shown, TLS is also moving in frequency. On the Ramsey time, this one was better than what we saw in our C Shunt flux qubits. This one was around 60 microseconds. There's not any real significant charge dispersion, and we can compare that with a similarly designed C Shunt flux qubit with only 2 parallel junctions, and this one had, I would say, a significant amount of charge dispersion. And another one of these rule of thumbs, as we know, is that the charge dispersion will go down as you increase the number of parallel junctions. And so here, going out to n equals 8 basically suppresses this dispersion effect. Now, the echo time that we measured was about 1.5 to 2 T1, and again, a little bit longer than the previous C shunts. This was primarily, though, due just to reducing the photon shot noise. And what I show here in the lower right corner are the T1 measurements basically interleaved with the T2 echo, and you can see that there is sort of a trend that both go up or both go down similarly. Okay, and then just to summarize the devices that we had made at that time, what I've shown is in magenta here. We got about, I should turn on a pointer. So we got about a gigahertz of anharmonicity on 3.6 gigahertz qubit. The coherence times were decent, I would say, maybe more impressive back in 2016, but still they were pretty good, and they were a little bit better than the C Shunt flux qubits. And the reason that they were better, I think, was consistent with this engineering framework that we were thinking about. You can see an even higher anharmonicity here, 1.6 gigahertz on 2.6 gigahertz qubit, but some of the T1s were not as high as we expected, and so that is something that we wanted to study further. And again, I think we will be picking this up again. So with that, I'm going to change and move on to a different topic, which is a different type of qubit called the composite qubit. So why would we be interested in small gap qubits? Well, we know that, basically from Fermi's golden rule, right, that the relaxation rates are going to increase with dipole moment and noise spectral density. So if we reduce that by lowering the qubit frequency, then we're going to, improve our decay rate or improve our T1. So that's one reason. Of course, that comes with the penalty of having to address excited state population. Now, off-resonant interactions, often also scale with a dipole moment, so this may be also an improvement. And the other is that operations, will use low-frequency baseband control rather than microwaves in the gigahertz range. And this, in principle, is simpler to calibrate. There's less crosstalk, and so these are a few motivational reasons why one might look at small gap qubits. And the paper I'm going to talk about is by Dan Campbell, and in this archive paper, but I also want to mention that David Schuster and Jens Koch and collaborators have an archive paper out about fluxonium, and maybe he'll talk about that today as well. Okay, so qubit control, conventionally, we all know we do Rabi driving basically to do single qubit operations generally, at least X and Y. And one requirement is that the Rabi frequency be much smaller than the transition frequency to avoid non-idealities, like the counter-rotating term. So this means that if you have a small qubit frequency, then the gates have to be slow, okay? And that's going to fight up against coherence times. So one solution to that is non-adiabatic Landau-Zener control, which enables you to do fast control for small gap qubits. And starting back in 2005, we did a number of demonstrations with a niobium qubit, which had a 10 megahertz gap. And that qubit had a T1 between 20 and 100 microseconds. So it was a very, very long T1 qubit, especially at that time. But the dephasing time was short. It was about 20 nanoseconds, and that's what limited it. Now, nonetheless, the idea of this Landau-Zener effect is that rather than just Rabi driving, you start at some point and then you just oscillate the tuning parameter, whatever it is in your system, back and forth through an avoided crossing. And this avoided crossing basically acts in some sense like a beam splitter, which takes the qubit state, splits it into two coherent parts, the excited and the ground state. You accumulate a phase. When you go back through the avoided crossing, then you can have quantum interference. Okay, and so we showed a number of interference experiments back at that time as a function of how far we sweep in voltage, how far we sweep, as well as where our starting point is. A couple of years later, we showed that we can actually do temporal control of a qubit in this way, so time-dependent control. And then later, some experiments, basically quantum emulation of scattering. In this case, it was a model of universal conductance fluctuations, but observed via scattering events at this avoided crossing. And then, of course, with a 10 megahertz qubit, you have to cool it to prepare it in the ground state. And we showed in 2006 that we can cool this qubit to colder than the dilution refrigerator temperature, whether it's 300 millikelvin or even 30 millikelvin. The qubit temperature we achieved at that time was about 3 millikelvin. Okay, so these...
Hey, Will.
Yeah?
For some reason, we can only see part of your screen. Would you mind just stop sharing and sharing again, see if that fixes the problem?
Yeah, sure.
Yeah, thank you.
Let's see. Let's see, is that better?
It's still the same. Not sure what happened. It was good at the beginning.
It's like clipping widescreen versus normal aspect ratio or something. So we're just losing the right and left edge. So we've got half of that plot on the right side is cut off.
All right, I guess the options are I could go to this mode, or we could just ignore it. What do you think? On my side, it looks fine, so I can't really tell how bad it is.
I think this mode is better because we at least see the whole presentation.
This mode is better, you said?
Yes.
Okay. Is that still visible if I make it this large?
Yes.
Okay. Yes.
Okay, I'll lose some animation, but that doesn't really matter, I think. Okay, so let me continue then. So the composite qubits are basically made from two transmon qubits, although it could be any qubit, but here we use two transmons of the Google style, XMON. So CQB means composite qubit. Composite qubit A are these two here. I guess you can see my cursor. And then composite qubit B are these two. And for each one, because it's two qubits, it's a 4-level system, but we're going to look at the coupled middle two levels that you see here for each A and B, and then A and B in turn are coupled via this capacitive coupling right here. So that's the starting point. Now, for the qubit spectroscopy, basically what we do is we have control over these two independent underlying qubits, and we can bias them basically wherever we want to create an avoided crossing when those two qubits become resonant with one another. Okay, and so that's going to be our qubit, and the splitting that we have here in this case was about 50 or 60 megahertz, but again we can choose that based on the capacitive coupling. And this is going to become the 2-level system now that we're going to do Landau-Zener type interferometry in. And so you can see the usual qubit, epsilon and delta. We're associating sigma z with delta because this is where the qubit basis is. And then what we're going to do is simultaneously drive both of those underlying transmons, transmon 1 and 2, to effectively operate and move around in this space. Okay. So the first thing we have to do is initialize the qubit, and I apologize that the animations won't work here, but basically with just a continuous wave microwave drive, this is the only microwave we need here, just a continuous drive, we then ramp the qubit, they're both in their ground state now, to the point where we can drive a transition. And then once that transition has been driven, we can turn off the microwaves, and then we bring this, the qubit bias to the avoided crossing, and that's where we started. Okay. So to do gates, basically Z gates are easy. They're just idling gates at the avoided crossing where epsilon equals 0, and then the duration of time that we wait, it's basically Larmor precession. You're precessing at a rate that is the qubit gap, and of course this already indicates that this gate is quite fast. Now, to tune up an X gate, it's basically the same type of Landau-Zener interferometry that we talked about before. We start at the avoided crossing, we detune, we come back through the avoided crossing, detune the other way, and come back. Of course, this has the nice feature that we don't have these offsets that we sometimes see when doing single-sided driving. It gets rid of the DC term. So we scan the drive frequency as well as the drive amplitude, and then we can find the places where we get basically a pi/2 pulse, and then we can fine-tune it from there. So just like with microwave driving, where we position this pulse will determine the axes on the Bloch sphere, and once they're set, then we have to respect them. So within a period of our drive, so T delta is basically 2 pi over delta, we decide to initiate a pulse at some time, and that will become, we'll just define that as our X gate. The solid line is plus X, the dashed line is the minus X gate. And when we're doing that, what we do is we end up getting some unwanted or additional Z rotation, which we then can correct at the end. So there's a little bit of an extra time that's required. So to tune up the X gate, we basically just concatenate these gates together, one after the other, to make a long sequence, and then this is basically an error amplification type approach to tune up the gate further. Now, to do the Y gate, we just have to shift Y in time so that there's basically a pi/2 phase shift between the X and the Y gates, and now we have both plus and minus Y. But the excursion is still the same. It's just the timing of when we start it. Now, we've looked at the coherence times in this device, and there are a couple. So the first one is you can look at relaxation from each of these logical qubit states to the ground state, and that's basically leakage out of the computational basis, and that's the major downside to this. I'll talk about that in a bit more. But what you see is that in the plots on the right are decays, whether you start in 0 or start in the 1 state, down to the ground state. And the upshot of all of this is that the decay within the subspace from 1 to 0 is greater than 2 milliseconds. And basically, that's just a very rough bound, because we're basically subtracting small, or basically subtracting two very large numbers to figure this out. So basically what's going on is that this, the CQB is a decoherence-free subspace, and relaxation within this subspace requires a correlated 2-photon decay, because each qubit, underlying qubit, has to flip. Okay, so it has a long lifetime, but unfortunately the leakage has a shorter lifetime, basically the independent lifetime of those two transmons. So we can do simultaneous randomized benchmarking, so doing it both to qubit A, so CQB-A and CQB-B at the same time, and we just do this by concatenating or bonding these types of X, Y, and Z gates together, just as you would do Clifford randomized benchmarking. And we, what you can see at the bottom is within the manifold, we're more than, almost 3 nines. And then out of the manifold, it's even a little bit better. I think this is all, basically 3 nines roughly. So the single qubit gates look reasonable. Now, there's a certain noise immunity that occurs here beyond just the obvious one. So of course, there's the obvious one that if you bias at a flux sweet spot, then fluctuations in flux, at least to first order, don't affect us. But it turns out that this CQB, this composite qubit, is first order insensitive to any noise source that fluctuates the underlying bare transmon frequencies, which you can see, just basically from this Hamiltonian here, that, you get this epsilon squared term, but now it's not just flux, it's basically anything that would fluctuate your underlying transmons is protected to first order. So to see that, this is basically protected against photon shot noise. And then I'll talk about leakage detection in a moment. So if we look at the decoherence rate as a function of the resonator photon number, then this is just the single transmons. They decay in the usual way. All right. This is 0, 1, 2, 3 photons. I'm not sure why the numbers didn't pop up. Okay, so that's basically what you would expect with transmons. But then with the CQB, you can see that it's a much, much lower decay rate. And that's because even though the resonators, each resonator may be fluctuating the underlying transmon, when it comes to the perspective of the composite qubit, it's protected to first order against that. Okay. Now, a consequence of this, or related to this, is that the individual resonators cannot distinguish the CQB logical states 0 and 1. And to see that, what we're showing here is the gate fidelity that we measured as a function of the resonator photon number, as basically just leaving the readout on. And what you can see is that even up to 2, 3, almost 4 photons, we're still at about 3 nines of CQB gate fidelity. All right. And again, the reason is that these individual resonators aren't able to distinguish the logical states 0 and 1. And if you remember back to the flux qubit days, when persistent current flux qubits were read out by squids, it was the same story, that the squid, when you were at the degeneracy point, couldn't distinguish between clockwise and counterclockwise circulating current. It was measuring in the energy eigenstate basis. And the only way to then measure was actually to detune and move away from the avoided crossing into a basis of persistent currents. And it's the same story here. When we want to read out this qubit, we also have to detune from the avoided crossing. But what this means is that while we're at the avoided crossing, these resonators, although they can't distinguish 0 and 1, they can distinguish the ground state, G, the true ground state, or both excited states as well, GG or EE. And so these resonators can be used to measure whether the qubit has leaked, right? You have leakage detection, but that leakage detection does not impact your gate fidelity within the subspace. So that's very useful, I think, and could be used to correct for leakage when it occurs. There are error correcting codes that can accommodate leakage, and they would have to be applied here. But we can detect leakage without leaving the avoided crossing. Okay, we did do 2 qubit gates. I won't spend a lot of time on this because it's basically similar to the 2 qubit gate you would do with a transmon. And you have a bunch of energy levels, as you see over here, but there's an avoided crossing with a level that's outside the subspace, and then you basically want to adiabatically go there, accrue a phase, and move out. Now, one interesting feature and difference of this is that these, composite qubit A and B can be tuned while staying at their avoided crossing. You don't actually have to leave the avoided crossing to do this tuning. There's a suppressed parasitic sigma Z interaction, which also is afforded by this approach. Despite that, there's some complications, and so we had to account for different basically make some corrective Z gates that did occur. And the total amount of time for this particular gate was quite long, almost 300 nanoseconds, and that limited its fidelity in part. And that was because we just didn't have a strong enough coupling between the composite qubits A and B. But within the manifold, we got about 0.8 fidelity, a couple qubits, and then out of the manifold, it was much higher. Basically, we ran out of time. Dan, fortunately, he got a job and left before we were able to tune this up. But there's no fundamental limit to the gate fidelity. I think with faster gates and better calibration, we should get better than 99%. And after we did this experiment, with just 2 transmons, we were able to get 99.7% fidelity. So I think we learned a lot about how to calibrate the 2-qubit gate. I'd like to go back and apply it to this. And so that brings me to the end. Let me acknowledge both colleagues at Lincoln and the campus, the Engineering Quantum Systems Group, and also LPS, Charlie Tahan and Yun Piddle Shim, with whom we did the composite qubit work. Okay, thank you.
Thanks, Will. That is really impressive. Now we have time for some questions. I see a question from John. John, do you want to just ask the question by yourself? And because I'm not sure which slide you're referring to.
Yeah, as in the chat, you were talking about your noise model. You talked about charge noise, and was that equivalent to loss in the capacitor? What's the physical mechanism there? I understand why you call it charge noise given the form of the Hamiltonian, but what do you think?
Yeah, that's right. So we basically called it charge noise, and it's charge noise only in the sense that it is a voltage fluctuation here. And the underlying microscopic mechanism, could be anything that leads to this, this voltage operator. So, what it is a good question. It's, TLSs certainly come to mind. Could be charge itself. But the purpose of this really was just to see if we could develop a model, an empirical model that would describe the results. And it seems like it worked pretty well.
Okay.
Okay, thanks, John. Any more questions from the audience? Right.
Yeah, I've got a quick question, actually, if you don't mind. Are you lumping critical current noise in with flux noise in this model, Will? Or is it's not a factor?
Yeah, so in this case, we didn't explicitly, look at critical current noise. I think it would could map into flux noise depending on how it's affecting the size of the circulating currents.
Thanks.
Hello?
Yes, Oleg.
Yeah, Oleg Astafiev. Will,
actually, I have a quick question for Will, too. If again,
let's take one at a time, Joe. Oleg, why don't you get started first, and we'll go to Joe.
Yes, okay. So you demonstrate this long times for shunted flux qubit, but my question is, if you still have some bad qubits or good qubits, so you demonstrated this maybe for the best ones, and what the scattering of parameters, or scattering of times depending on qubits?
Yeah, so what I want to emphasize is in this middle plot here is that we intentionally varied the parameters over a wide range. If you look in the upper right corner here, these 4 qubits were basically identical to one another. And so this gives you an idea of the fluctuation in the coherence times that we measured. And then, of course, it's impacted by the quasi-particles. And so we have to pump those away to make some statement about what's the underlying temporal variation due to other mechanisms besides quasi-particles, et cetera. So I don't have a number that I can quote, but I can say that the C shunt flux qubits generally, we see them with times between, T1 times between, say, 20 and 60 microseconds when they're designed in this way. And then the T2 times with an echo are about 1.5 to 2 T1. The Ramsey times, they tend to be on the order of T1 or a little bit less, actually. They generally are that way. But the reproducibility is much better than the underlying, the old persistent current flux qubit. That's for sure.
Oh, thank you.
Thanks, Joe. No, sorry, thanks, Oleg. We have one more question from Joe, but Joe, in order to keep the things on schedule, do you mind to push that all the way to the end? We have a discussion section there, and you can ask Will in more depth.
Sure. It should be a very quick question.
Okay, go ahead.
I was just going to ask, we mentioned that for the CZ that you could keep the qubits and the composite qubit at degeneracy. Are you just sweeping both flux biases on those two coupled qubits simultaneously, basically?
Yeah, that's right. So anytime we want to change the qubit frequency of a composite qubit, we have to simultaneously apply flux biases to both underlying transmons. And that's 2 transmons per composite qubit. So if we do coupled composite qubits, we're actually simultaneously biasing 4 underlying transmons.
Thank you.
Okay, thank you, everybody. Appreciate the question.
Thank you, Will. If you have more questions for Will, we'll have a dedicated discussion section at the end. With that, we'll move on to Fluxonian, and we'll have Vladimir from University of Maryland to tell us their recent progress.